Welcome back to this lecture series on pulse width modulation for power electronic converters. We were looking at various power electronic converters and then we were looking at the essentials of pulse width modulation such as Fourier analysis and all. We were looking at low frequency PWM, we were looking at selective harmonic elimination and certain optimized offline PWM. Now, we are talking of more of real time or online PWM, where the PWM generation is done in real time and at a high switching frequency. In the last class we started off with sinusoidal modulation. So, today we would try to do a little more on modulation. Now, it is going to be a harmonic injection pulse width modulation now. So, it is a little interesting. I have often been asked this question, Professor, you eliminate harmonics earlier in that selective harmonic elimination classes, but now when you come to this harmonic injection you seem to be injecting harmonics. Well, to put it jocularly, I would call these harmonics as friendly harmonics, that is these harmonics are harmonics, but they really do not matter. I mean they will not affect the performance of your motor drive. So, that is how it is going to be. So, let us see what kind of harmonic injection is being done now. It is actually going to be some kind of second harmonic injection for the single phase inverters, and it could be 3 phase. I mean the more useful case is third harmonic injection in the case of 3 phase inverters. So, let us just get started. So, once again if you go through the basics, this is a voltage source inverter, and in the case of voltage source inverter what you have, it is essentially there is a load. This is a single phase voltage source inverter. So, there is a load and the load has 2 terminals and the load is presumed to be inductive, and therefore, every terminal is connected to a pole and there is a single pole double throw switch. Once again you have a single pole double throw switch. There are 2 single pole double throw switches as we know, and these single pole double throw switches are realized using these kinds of transistors. So, what do? We switch these transistors on and off in a complementary fashion. If the top is on, the bottom is off and vice versa. The same way we can do this, and both these legs can actually be controlled independently. All right. So, in the case of the so called bipolar PWM, what we do is we keep these 2 on and the other diagonally opposite switches off. That would apply VDC with particular polarity, and in the other way what you do is you apply the other diagonally opposite switches are kept on and the other 2 are off, that applies minus VDC. So, this plus VDC and minus VDC can be applied across the load for varying durations, and that is bipolar PWM, because between this VAB output in the positive half cycle as well as in the negative half cycle of the fundamental voltage, you see positive pulses as well as negative pulses. That is what we saw in the last class. So, that is the bipolar PWM, and we would use the more popular unipolar PWM. So, if you go to that unipolar PWM, now first let us just look at one leg and one sine wave corresponding to a leg now. So, why do we use a sine wave? The idea is the average pole voltage, that is you had the pole before, you had the pole, the voltage at this pole we want it to be modulated in a sinusoidal fashion with respect to the DC bus midpoint. That DC bus midpoint is not indicated here. You can regard this VDC as VDC by 2 and another VDC by 2, and the midpoint can be regarded as O. So, that is the DC bus neutral. So, if you modulate this A, average voltage at A in a sinusoidal fashion, and also modulate the average voltage at B in a sinusoidal fashion, the difference between the two will certainly be a sinusoid. So, that is an idea. So, now you use a sinusoidal signal. So, you use a sinusoidal signal. This is for one of the phases now. So, what you do with that? You actually compare a triangular carrier. This is a high frequency triangular carrier. As I said, you have indicated I have considered a frequency of 9 times the fundamental. It could be bigger, much bigger than this at nominal power levels, like a few kilowatts, etc. It can be, if it is IGBT inverters, this carrier frequency can be as high as 15 kilohertz to 20 kilohertz. In case of MOSFET inverters, it could still be higher depending on what is the rating that we are talking of. In very high power levels, this could be lower. That is, for example, where you use IGCTs or GTOs, this carrier frequency could only be a few hundred hertz. So, we have a model and we regard this, for all purposes of the study, we regard this carrier signal as a high frequency signal whose frequency is much higher than that of the modulating signal. So, that in one carrier cycle you can regard the modulating signal to be almost flat. So, there is any change that you have, that can be ignored now. So, you have the high frequency in the when you are considering high switching frequency, you can always look at the average pole voltage concept. So, what is this average pole voltage concept? Now, you have VAO, and this VAO is equal to either VDC by 2 or minus VDC by 2, where O is the midpoint of the DC bus. When A top device is on, this voltage is equal to plus VDC by 2. When in A bottom device is on, only one of the two devices can be on, So, when the bottom is on, it is going to be minus VDC by 2. So, what do you do is, in a small interval of time which is equal to the half carrier cycle. So, what you do is, you sometimes apply plus VDC by 2 and you apply VDC by 2 for the remaining duration. So, you have certain average voltage, I put it as VAO, this is the average value. Average value of what? Average value of VAO over what interval? Over a half carrier cycle, one half a cycle of the carrier. So, for half a cycle of the carrier, what happens? You apply VDC by 2 for how long? For whatever is the duty ratio, D times Ts. Then you apply minus VDC by 2 for the remaining duration, which is 1 minus D times Ts, and you average it. Your average pole voltage will be equal to VDC by 2 into D minus VDC by 2 multiplied by 1 minus T. This is what is going to be your average pole voltage. So, this is the average pole voltage, this is the relationship between the average pole voltage. What do we mean by the average pole voltage? Pole stands for the pole of the single pole double throw switch. Every leg is a single pole double throw switch. So, the pole refers to the midpoint or one of the load terminals, and we are talking of this pole voltage. That pole voltage is measured with respect to O, that O is the DC bus midpoint, and we are talking of its value averaged over a half a carrier cycle. So, what you are trying to do is, sometimes you are applying VDC by 2 and sometimes you are applying minus VDC by 2. How do you exactly do that? For example, let us say you consider a half carrier cycle. This is one half carrier cycle. I have drawn the carrier waveform here, and now this is your modulating signal. This is your modulating signal. Now, let me call this as plus Vp and this as minus Vp. These are the positive and the negative peaks of the carrier. That minus is not clearly visible. This is minus Vp now. So, what do we do when we are switching? Whenever the modulating signal is greater than the carrier. Now, I have regarded the modulating signal as a DC. Why? Because we are looking at a very short interval of time. It is much shorter compared to the fundamental cycle, and therefore, you can ignore whatever variation that you have in the sinusoid, or you can take it is the sampled value of sine. So, it is a flat line now here. So, what do? You compare this sampled sine wave and this carrier. So, now whenever the sine wave is greater than the carrier, the top device is on. So, that means during this interval you have plus VDC by 2 is applied, you have plus VDC by 2 applied, and during the rest of the interval it is minus VDC by 2 is getting applied now. So, let me change the color. So, this is right. So, let us redo that with plus Vp and minus Vp clearly. So, this is plus Vp and you have minus Vp, and then I have the carrier signal, I mean I have the modulating signal. This modulating signal I will draw like this, and this value let us call it as MA. This is the modulating signal corresponding to A phase now. So, let me draw dotted lines here. This is the starting of the interval, this is the ending of the interval. Now, what is the voltage that you have here? During this up to this instant you have VRO is positive and here VRO is negative. This is VRO, and VRO here is plus VDC by 2, here it is minus VDC by 2. And where is the 0 line? Somewhere like this. This is the time axis. So, what you are applying is, as I said, this VRO plus VDC by 2 is applied for certain duration of time, and that duration of time we call this as the duty ratio times whatever Ts. Ts is the half carrier cycle, and this remaining time is 1 minus d times Ts. This is a more detailed explanation of why I have written this equation this way. So, this is how you do a comparison. Therefore, you have Vdc by 2 times T and minus Vdc by 2 times 1 minus d. This is your average voltage now. So, I have expressed this average pole voltage in terms of duty ratio. Let me try and express it in terms of MA. How do you do it in terms of MA? First, let us say this is the duty ratio D. How is the duty ratio D related in terms of MA? For a duration of time equivalent to MA minus of minus Vp, the top device is on. For the remaining duration equivalent to Vp minus MA, the bottom device is on. So, I can say MA minus of minus Vp, that makes it MA plus Vp divided by 2 Vp. This is the duty ratio. This is the time for which the top device is on now. Let us just simplify this expression, or I mean just split it up. This becomes plus half. So, this is how duty ratio is related to the modulating signal value and Vp, that is the peak of the carrier. If we take peak of the carrier to be 1, you can simply call it MA by 2 plus half now. So, let me write it the other way. If I take it this 2d, I am taking this 2 in the denominator to the other side, minus 1 is going to be equal to MA upon Vp, is that right? 2 goes off to the other side. So, it is 2d. So, what you have is MA by Vp plus 1. So, 2d minus 1 is equal to MA by Vp. So, what is this expression exactly? VAO average, VAO average, there is Vdc by 2 times d minus of Vdc by 2 and there is minus d. So, this is exactly what you have here is, let me go back, VAO average itself is Vdc by 2 times 2d minus 1 from the previous equation, and that is nothing but Vdc by 2 times 2d minus 1 is equal to MA by Vp. So, we have the average pole voltage related in terms of DC bus voltage and duty ratio first, and duty ratio is related in terms of the modulating signal and the peak of the carrier. And once again, you know, this is the other these two are related like that. This here the duty ratio is expressed in terms of MA, MA in terms of duty ratio. So, what you get this is VAO average is expressed in terms of MA and Vp now. So, you can say your duty ratio the average pole voltage is Vdc by 2 times 2d minus 1, or it is Vdc by 2 times MA upon Vp in terms of the modulating signal now. Now, this modulating signal is sinusoidal. MA is sinusoidal for us here. So, if MA is sinusoidal, you are going to get a sinusoidal average pole voltage. That is the idea. This is what you do. Now, this is the idea of using a sine wave also. The average pole voltage varies in a sinusoidal fashion, because this MA that you have here is a sinusoidal signal. So, we can call it some Vm sin omega t or so, and you go about doing that now. So, this is your average pole voltage now. Why do you do this now? If you have VA as average pole voltage, now I may rewrite it here. So, excuse me. So, I have VAO is what? MA by Vp times Vdc by 2. My MA can go as high as Vp, not beyond that. That would be called over modulation, and you know it will just get clipped to Vp in any case. So, the maximum voltage that this is the average pole voltage, the maximum value of the average pole voltage can only be up to plus Vdc by 2. The minimum voltage can be minus Vdc by 2. So, the maximum amplitude it can take is Vdc by 2. So, VAO average can be Vdc by 2 sin omega t if you wish. Now, what is VBO average? VBO average is similarly, instead of the A leg, for the B leg we have another sine wave, and that divided by Vp times Vdc by 2. And what is your VAB average that is applied on the load? What is applied on VAB average is actually VAO average minus VBO average. This is what you apply. Is that right? So, this is a sinusoid, that is a sinusoid. So, here what do we have? VDC upon Vp to Vp, let us call it some Vm sin omega t, and what we have here VDC upon 2 Vp. So, the MB is also a sinusoidal signal of the same Vm, and it is also sinusoidal signal, same frequency, but it is phase shifted by 180 degree. In the case of a 3 phase inverter, this will be phase shifted by 80 degrees now. So, VAO average will be a sinusoidal waveform. So, if VAO average could be a sinusoid like this, that can be regarded as a phasor. And what would be the amplitude of this phasor? The maximum value it can take is VDC by 2, and this VDC by 2 is multiplied by Vm upon Vp. This Vm upon Vp is usually called modulation index by many people, because it gives you how much of AC voltage you are really trying to produce. And then where is your VBO? Same, this is, except that it is in the opposite direction. I am writing it as capital VAO and I am writing this as capital VBO. By this I mean that VAO average essentially, which is only a sinusoidal quantity. We can do a phasor sum. So, if you do the phasor difference, what happens? Essentially this is your V, this sum of the two, this is your VAB, right. So, you get this, how that is how you subtract this now. If this were a 3 phase situation, what you will have is, we will have a VRO, average pole voltage, and we will have for Y phase there is one average pole voltage, for B phase there will be one average pole voltage, and those average pole voltages will be phase shifted by 120 degrees now. So, this is what we have in terms of sinusoidal modulation now. In case of single phase inverter, in case of unipolar PWM, we are going to use just an MA and MB, both are sinusoidal signals at the fundamental modulating frequency, both have the same amplitudes, but they are the sine inverse of one another, they are phase shifted by 180 degrees now. So, there are certain possibilities, different waveforms are possible. This is what we are trying to do. What we are trying to see is, this is what you are trying to get. What is that? The top waveform represents VAO, this is the MA, the modulating signal for leg A. Black waveform represents the modulating signal for phase B, or it is the modulating signal for phase B. The red signal represents the average pole voltage of A leg. The black signal represents the average pole voltage of B leg. What does the difference between the two represent? What does the difference between the two represent? The difference between the two represents the average load voltage. It is the difference between the two. So, essentially what you can say is, let us say the A phase voltage is slightly shifted up by a small amount. Let us say, on this scale, let me say it is about 0.01, and the B phase is also shifted slightly above by the same to the same extent, say the same 0.01. So, what will happen? The A phase signal will not look like sinusoid, it may be phase shifted, or it could be some other signal also. Again, B phase signal also will not look sinusoid, I mean maybe, or it is a level shifted sinusoid or whatever, but the difference between the A leg and the B leg remains unaffected. The average output applied on the load is unaffected. So, A can be shifted slightly up and B also can be shifted slightly up, that is what is called as common mode now. So, if you look at it in terms of the inverter, what happens? It is closely related to the redundancy of the inverter now. So, here even if you do this, this is the average output voltage. What is this average output voltage? This average output voltage is the average pole voltage of A leg minus the average pole voltage of B leg. So, if they are simply sinusoids as shown here, and with certain small amount of common mode added to both of them, it would be the same, right. Now, let us say what is that common mode, why does it come up? What if you look at a 3 phase inverter now, in a 3 phase inverter, now first a single phase inverter, we are still looking at a single phase inverter. You have a load output, let us call as VAB. VAB can be equal to plus VDC, and it can also be equal to minus VDC, it can also be equal to 0. When is equal to plus VDC? When the top device of one A leg and the bottom device of B leg are on. When it is minus VDC, the opposite situation. When is 0? There are two things, both the top are on, both the bottom are on, that is both SA and SB, both of them can be high, or it can be SA bar or SB bar. meaning both the signals can be low. In all these cases you have this issue. So, if both the top is on and both the bottom is on, in both the cases you will have this situation. So, why so now there is a redundancy, this is what we call as a redundancy. The output voltage is the same, but it can be applied in two different ways, right. There are two different inverter states which apply the same output voltage. Now, this is what you would call as redundancy. Does not matter to the load just sees a short, but it matters to the inverter, because which device conducts and which device does not conduct depend upon which of the two states that you have used now. So, this redundancy is closely related to what we are trying to do. Let us see what we are trying to do a little further. Now, we looked at the sine waveform, we looked at this earlier. On the same thing, let us say I do an MB also, there is B phase also, correct. Let me take another color and let me call this as MB. So, earlier we were seeing only one signal, now we are seeing two different signals, that is I am showing the second leg signal also. If I am doing my MB like this, what would be the B phase voltage? I am sorry, this is not VRO, this is VAO. How would VBO look like? VBO would look like something like this. VBO would look like something like this. It will be plus VDC by 2 for a short duration and then it is minus VDC. So, this green color is VBO. Now, what are the inverter states applied? If I take the first interval when both MA and MB are higher than the carrier signal. So, I would write it as plus plus, meaning in both the legs the top devices are on. Then in the second case, if I see in the second interval what happens, the B leg switches, but the A leg remains unchanged, it is like this. If I look at the third interval, what happens? Both of them are negative. So, this is the same situation would prevail if I shift MA and MB up by a small extent, or both MA and MB down by certain small extent now, as long as the extent of shifting up or down is very small now. If I shift up or down, what happens? Let me indicate that here. I can shift this up or down, I can shift MA also up or down by a small extent, that is what is called as common mode injection now. If I shift up or down both to the same extent, what happens? You have this distance between these two. The distance between these two is unchanged. So, that is really the pulse width for which the VDC is applied. This is the duration for which the actual voltage pulse is applied across the load, and in the first interval the load is shorted and the third interval is also load is shorted. If both MA and MB are moved a little upwards, what happens is the time for which this plus and plus applied is a little longer and the time for which this minus and minus applied is a little shorter. There are only changes in these two intervals. These two intervals change, but the middle interval remains unchanged. If interval plus plus increases, the interval minus minus decreases now, that is because of the redundancy. So, you can apply 0 voltage to the load either by switching both the top devices on or having both the bottom devices on. So, this is what you are doing. So, when you are adding common mode voltage, the time for which you are using both the top devices and the time for which you are having both the bottom devices conducting, it changes. So, that is why I said it is related to the redundancy. The redundancy of this is what lets you to add such a common mode voltage. So, this is what we mean by redundancy. So, these two legs can change and you can go about doing now. So, what you can do is you can consider adding certain common mode signal, that is you have your MA. This MA you can call it some MA star, which is equal to MA plus certain MCM, which is a common mode signal, and then you can look at MB star, which is equal to MB plus the same common mode signal. As long as the common mode signal is small, right? How small is small? The sum of these two, MA plus MCM, the new MA star, at any instant of time on the line cycle should not go more than plus Vp, the positive peak of the carrier, or should not go below the negative peak of the carrier. As long as you do that, what is the purpose in doing that? We will discuss it later. There may not be any purpose also, but I am trying to say theoretically it is possible for you to do this on account of the redundancy by adding this now. The next thing is, what should this common mode component be if it should be the same? The common mode component could actually be a small amount of DC, and if you see, it can also be a small amount of AC, because what is the difference between AC of what frequency? Of double the frequency of the fundamental. Why so? What are you getting? MA and MB. What is the relationship between MA and MB? What is the relationship between MA and MB? They are phase shifted by 180 degrees. So, if you add an even harmonic component there to MA and phase shifted by 180 degree, the even harmonic component is just going to remain the same, and when you do a subtraction, the even harmonic component will vanish. Let us look at closer examples in the next slide or so. So, we first add the bipolar PWM, which is the simplest way of switching. Only the two diagonally opposite switches are on at any point of time. The control is very simple, but the harmonic distortion could be very high in this, right. The unipolar PWM is reasonably good. I mean, that is probably what you can regard as standard technique. If you want to choose one technique, I think most probably you would go and choose a unipolar PWM, unless you have any reasons to shift to something else. I would call it as a default option for somebody who might work with single phase inverters. Okay. Now, there could be reasons why you want to choose something else. Now, on this unipolar PWM, it uses two different sine waves. On that, it is possible to inject a even harmonic. If you add an even harmonic, what happens? That's a common mode component there. You add a small even harmonic. I am going to demonstrate it in the next slide. And this also can lead to what is called as bus clamping. So, that I will talk about a little later. The kind of even harmonic components can be added could be such that it leads to bus clamping, that is, one of the legs not switching for certain amount of time, but continuing to remain clamped to either the positive bus or a DC negative bus for some amount of time. So, let us look at this even harmonic stuff. Now, the dotted lines that you have, the red phase, and then the dotted lines you have, the black, are the A and B leg original sinusoidal signals. On top of it, what I am trying to do is, I am just trying to add this blue signal here shown in dashed lines. What is that? That is common mode, and that is actually, you can see that it is double frequency. It is an even harmonic, it is a second harmonic to be very precise now. I add the second harmonic as a common mode component to both my red phase and the black phase. So, what happens here? You see that the actual modulating signal is now different. An actual modulating signal for the black phase is different now. Would this affect the output? No. Why? Because the red signal is the average pole voltage for A phase, and this black signal is the average pole voltage for B phase, and the difference between the two is unaffected. VAO average is changed, VBO average is changed, but the difference between VAO average and VBO average is not changed. That is going to remain the same as what we saw before. That is the same kind of sinusoid that we had here. Same kind of sinusoid that we had here. So, you have this. Is there a point in adding it? It could be a question. Just hold on. There may not be a point, but a similar third harmonic injection is possible in the 3-phase inverter, and that is pretty much valuable. So, let us see what we can do about this now. So, all I can say is you can add a second harmonic like this of a small amplitude, and you see that the red phase thing increases, the black phase negative peak goes down further. Here again the black phase thing goes further. So, the peak values are going, the modulating signal is no longer quarter wave symmetric. Earlier the sine wave is nicely symmetric about its peak, about 90 degrees, now it is no longer so. So, all this happens, but it is okay, but the final output voltage will be unchanged now. So, there is no point essentially, you can, but nevertheless you can add a small value such that this peak value or this peak value do not go beyond plus Vp or minus Vp now. Okay. So, now it is possible to add fourth harmonic like this, sixth harmonic, eighth harmonic or anything, any even harmonic really like this now. You can add that in such a fashion that any signal which is at double the frequency. Now, this you see this blue signal, what is this blue signal? What is the frequency of this blue signal? Twice the modulation frequency. You see the red sinusoidal wave, that if you call it as 50 hertz, this blue is at 100 hertz now. You add this blue signal to both of this. How have I derived this blue signal in the first place? I have subtracted 1 minus the red phase sign to get the blue signal here. What I have done in the second half cycle, I have subtracted this black, this is from minus 1 here. So, I have got the same kind of difference between these two here now. So, now what I am trying to do is, this is, I am adding this blue signal, I am adding as common mode to both red and black. So, what happens? The red signal goes and gets clamped here, and the next time around what happens, the black signal goes and gets clamped here. What do I mean by clamped? The modulating signal becomes equal to the carrier peak, therefore, there are no intersections and the positive device of A leg is continuously on here and the top device of B leg is continuously on here. So, A leg does not switch at all here, so it is low on switching losses. Again B leg does not switch at all here, it is low on switching losses. When switching frequencies are very high, every time you turn on and turn off, there is certain amount of energy lost. When the switching frequency is high, the switching loss is going to be high. We will do some detailed calculations a little later, some few lectures away, but now you can just see this now. So, what it does is it saves certain amount of switching loss for you, energy lost on account of switching A leg. Here you save certain amount of energy on account of by not switching the B phase leg now. So, this is what is called as bus clamping, because A phase remains clamped to the positive bus here and B phase gets clamped to the negative bus here. Now, you call it as bus clamping pulse width modulation now. Okay. So, it can reduce that the switching loss, but is it desirable? There is something that you have to observe now. You see that the top device is conducting here, and in the second half both the top and the bottom devices could be conducting. So, you see that the top device is conducting for longer time than the bottom device in the A phase leg. The same way in the B phase leg, in this entire half cycle the top device is conducting, whereas in this half both top and bottom are conducting. So, overall again in the B phase the top device is going to be conducting now. So, this is a situation where one leg, in every leg the top device is going to be heated up more, there is going to be more loss in the top device than in the bottom device. That is what I mean by unequal loading. The heating of those devices, the top and the bottom devices are going to be different, and that is not very desirable, because by and large you would choose devices which are equal, it's they have the same rating. So, if you are going to heat up one and not use well or the other one, that is not an optimal utilization of the devices that you do. So, this bus clamping is good insofar as it reduces the switching loss, but this is not good enough because the losses in different devices are different. So, now what we are going to look at is we are going to see whether we can make these losses equal. That is what is being done here now. How do you do that now? Here I have just derived my common mode a little differently. You see that this is common mode and you see this is how it is. You can see it is periodic over 180 degrees. You can see its fundamental frequency is 2 times the actual fundamental modulation frequency. Now, how do I derive this? I have subtracted 1 minus this. I mean I am taking A phase and taking the difference between that and here some time. Here I am taking the B phase. What I have done is I take the difference between B phase and this other signal now. So, I go about doing that. So, either A phase or B phase I choose and I subtract. If the signal is going positive, I subtract 1 minus that signal. If the signal is negative, I am subtract minus that signal from minus 1 now. So, this is basically a result of subtraction of from plus Vp or minus Vp a particular leg signal. So, this you get it like this and this you get it like this. When this common mode is added to the 2 leg signals, A signal changes as shown in the solid line here. It is no longer sinusoid, it goes down. Here it is clamped, it goes down like this now. So, what are we achieving now? Here in this 90 degrees duration, A phase top device conducts. In this 90 degree duration, it is the bottom device is on and the bottom device conducts. So, the switching loss is reduced. A phase switching loss is reduced by 50%, because 50% of the time A phase is not switching, and the conduction losses are also uniformly distributed between the top and the bottom device. Similarly, you take the leg B, which is shown in black ink now. During the first 90 degrees, it is the bottom device of leg B that is on. During the last 90 degrees shown here, the top device is on. So, there is no switching loss here, there is no switching loss here also in B phase leg, and the conduction of the 2 devices are more or less equal, and you end up in equal loading of devices. So, this is one way. So, what you are trying to do is you are adding some even harmonic injection. This is not just second harmonic, this is not a sinusoidal waveform. This waveform is at a fundamental frequency of 100 hertz. If the sine is taken as 50 hertz, the blue waveform is at 500 hertz. So, what are the frequency components of the blue waveform? 100 hertz, 200 hertz, 300 hertz, 400 hertz, 500 hertz, etc. So, it has lots of all the even harmonic components here, 2, 4, 6, 8, everything is there now, but it does not have DC in this, as you can see in this case now. That is a requirement, otherwise it could end up in uneven loading of the top and bottom devices. And also you see that these two waveforms are actually similar, the red waveforms and the black waveform, you see similarity between the two, right. So, what you get is you have the equal loadings of the two legs and also for the top and bottom devices now. So, you are able to add this kind of blue common mode signal and you are able to reduce your switching energy, because you are switching at very high frequency, you may want to reduce that. So, this has the benefit of giving you a lower switching loss and also equal kind of devices here now. So, this is in one of the references which I will give at the end of this lecture, which I also indicated in the previous lecture. So, the same thing this is slightly differently done, that is the choice of phase, which phase Vp subtracted from etc. is different now. So, here what I am trying to do is from 1 I am subtracting this to produce over the first interval, and then I am using the next phase, I am subtracting it from -1 to produce the next one. So, I get my common mode signal like this. So, now the common mode signal, the blue signal is different, but you can see that it looks very similar, it is just flipped around excuse me. And so, this is what you have. Now, here A is clamped here, the top device is conducting continuously for 90 degrees and the bottom device is continuously conducting for 90 degrees now. So, A phase does not switch for half the time. So, switching energy is saved, I mean the loss on account of switching is saved, and the conduction is also uniformly distributed between the top and bottom devices and also between the two legs. So, you by even harmonic injection you have no advantage, but you can possibly have this advantage. What you can do? Bus clamping, that can result in lower switching energy loss, and also ensure that by and large there are several methods. These methods are relatively not so widely known, that is bus clamping methods are known, but bus clamping methods for single phase inverters which would result in equal loading of devices are not so very widely known. It is contained in one of the references that I have given there now. So, some comments on the even harmonic now. It is possible to add even harmonic. What do? You can add even harmonic. There are two sine waves for A leg and B leg which are phase shifted by 180. You can add a small amount of even harmonic, provided the peak values of the two waveforms do not go beyond plus Vp or minus Vp. So, that does not affect the output voltage as long as you add it in small measure, because the difference between the two modulating signals should still be the same. And if you add it properly, if you derive your common mode voltage properly, it is possible that you could ensure bus clamping, and if you ensure bus clamping you can reduce switching loss if necessary. So, and bus clamping has to be done in such a fashion that it ensures equal loading of the top and bottom devices, which is what we tried and ensured now, and also equal loading of devices in the two legs. So, this is what we have done now. There is one assumption here which I have given at the end here. What is that assumption that I am giving here? The thermal time constant of devices is longer than the line cycle. That is, what is your basic assumption? You go forward. Here this is not conducting, that is one device is conducting and here another device is conducting now. Because it is conducting, there is certain amount of loss, heat is being dissipated now, and this this heat is going to increase the temperature, but there is a delay between the junction temperature rise. The junction temperature has some maximum safe maximum value. When the device conducts or because of switching action, the device dissipates energy. When it conducts, and therefore it dissipates power, and in this region the devices are switching, and on account of both switching and conduction there is some power dissipated now. This results in increase in the junction temperature, but there is a delay. The moment there is power dissipation, your junction temperature does not increase, there is a delay, and that is what is called as thermal time constant. There are various time constants involved there. So, there is certain thermal time constant now. So, what we assume is what is true in most practical cases. In most practical cases, this is like 50 hertz, like 20 millisecond cycle, or maybe 60 hertz in some countries, and you would want to vary in the variable frequency used, you may come down to 5 hertz or whatever now. So, if your nominal frequency is 50 hertz, you are talking of 20 milliseconds now. The thermal time constant is much longer than the line cycle time. That is the fundamental assumption here now. So, at 50 hertz if you are doing it is very valid now. So, it does not heat up. So, in an average sense the device losses are reduced now. If you are going to do a switching not at 50 hertz, but at something like 0.5 hertz or 0.05 hertz, you better be very careful now. So, this entire thing that you got here, the previous one is based on the assumption, this bus clamping is based on the assumption that the thermal time constant is longer than the line cycle time. If that is not valid, you really can't go in for bus clamping. and in most cases when you are switching, the modulating frequencies like 50 hertz, 40 hertz, 30 hertz, it's a perfect assumption, right. So, we go forward now. So, what do? We do look at a 3-phase voltage source inverter now. So, it is the same thing, we just dealt with this even harmonic primarily to prime ourselves to deal with this problem of 3-phase inverter, adding common mode injection or third harmonic injection in 3-phase inverter, and that is a very significant practical problem. It has great theoretical and practical significance. So, we just prepared ourselves by going through single phase inverter which has only 2 legs before we tackle the problem of 3 legs now. So, you have 3 legs and all the 3 are single pole double through switches, and they are realized in terms of switches which switch in a complementary fashion as we know. So, what we do now, in the case of unipolar PWM for single phase inverter, you simply use 2 sine waves which are phase shifted by 180 degrees. Now, what we are doing? We are using 3 different sine waves, and the sine waves, what is the frequency of the sine wave? It is that output modulation frequency that you desire. And what is the amplitude of the 3 sine waves? They are equal. And how about the phase? They are phase shifted by 120 degree each. This is the red phase R, this is the Y phase, I have just given it in green for clear visibility, and this is the blue phase B. You phase shift R by 120 degree, you will get this Y phase signal. You phase shift this by 120 degree, you get this B phase signal. So, these are 3 phase sinusoidal modulating waves. What you could do is, you do this, you can compare this with a high frequency carrier that goes up and down like the arrow that I am showing there, right, it moves up and down, a very, very high frequency carrier you can compare. Same carrier for all the 3 modulating signals, and whenever the modulating signal of a phase is greater than the carrier, you switch on the top device. Whenever the modulating signal is less than the carrier, you switch on the bottom device. That is the simple logic as we discussed in the last class now. Now, once again in 3-phase inverter there are redundancies. What is the redundancy? Very, very similar to what you had in case of a single phase inverter. That is, when your load is being shorted, you can have the situation what I would say as plus plus plus. What I mean by plus 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 is R phase, Y phase and B phase. The R phase top device is on, Y phase also top device is on, B phase also top device is on. All the pole voltages are plus VDC by 2, plus VDC by 2 and plus VDC by 2. What is the difference between those two? What is VRY? 0. What is VYB? 0. What is VBR? 0. So, this is what is called as a 0 state. The line to line 3-phase line to line voltage is 0. You are shorting the load. The load is just being, there are only a freewheeling path is being provided for the load now. So, it is being done by keeping all the top devices on. This is not the only way to do that. There is yet another way of doing it. What is that? You keep R, Y and B in all the 3 legs, you have the bottom devices on. This is again would ensure that the load is shorted. In this case, VRO, VYO and VBO are all equal to what? Minus VDC by 2. Nevertheless, all the 3 line to line voltages VRY, VYB and VBR are equal to 0 and the load is shorted. So, as far as the load is same, plus 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 is one inverter state, one 0 state, and minus 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 is another 0 state. These two are the same as far as the load is concerned, but as far as the inverter is concerned, it makes a lot of differences now. In this, I mean, in the sense, here the top devices are on, here the bottom devices are on. So, in the first case, the top devices are going to be suffering loss on account of conduction. In the second case, the bottom devices are going to be suffering loss on account of conduction now. So, the normal thing to do is use both the states, that would be the conventional wisdom, and also you do it equally, and that is what you do in conventional space vector PWM, which we will discuss a few classes later now. So, you will see that there is a redundancy. The same way the 0 applied, there are 2 different states that was possible for you. Here also there are 2 different states are possible now. The poles can be connected, all the poles can be connected to the top throw, all the poles can be connected to the bottom throw. That is how it turns out to be now. So, that is a redundancy now. Because of this redundancy, what happens now? Let me take this thing. Let me first choose, let us say, black ink, and let me draw a half carrier as I did before now. Then let me choose red ink and draw the carrier, I mean the modulating signal. Did I choose red? Yeah, I think that is a different version of red. So, alright, this would be proper. This is what I would call as M or the modulating signal corresponding to R phase in this carrier cycle. As I said, the carrier cycle is much shorter than the modulating cycle, signal cycles, therefore, modulating signal is a flat line here. Then let me just go and indicate the Y phase signal. let me say this is Y phase signal, and then there is a B phase signal. Let me indicate it with blue. So, like this. If MR, MY and MB are sinusoidal signals, then MR, MY plus MB should add up to 0. So, what you really have here is this is plus Vp, this is minus Vp as before. So, earlier you had 3 different intervals, now there are 4 different intervals now. So, first there is an interval here, this to this. During this interval, what happens? All the 3 phases, their signals are greater than the carrier signal. Therefore, what you have is all the top devices are on. The inverter state there is plus plus plus, you can call that inverter state as plus plus plus, and the output is 0. All the 3 line to line voltage is 0. Then you have a second interval like this. During the second interval, what happens? R phase continues to be high, yellow phase also continues to be high, but B phase has now gone negative. Then there is a third interval. During the third interval, what happens? R phase is high, yellow phase is negative, B phase is also negative. What happens during the last interval? All the 3 are minus minus minus. This is what happens now. Once again, you can think of a common mode. By common mode, I mean I would shift MR slightly above, MY slightly above and MB slightly above, and such that it does not go beyond Vp. In this carrier cycle or in any of the carrier cycles, it should not go beyond that. That is how I add a common mode signal. When I add a small common mode signal like that, what is going to happen? MR shifts up, MY shifts up, MB shifts up. Therefore, the first interval will get a little longer because MB has shifted up. The second, the switching instant will delay, but the interval will not change because the difference between MB and MY hasn't changed. And similarly, the third interval also would not change because the difference MY and MR, there is no change in that, their difference is still the same, and the last interval will shrink. So, the first interval will increase at the expense of the last interval, or if the signals come down, it will be the other way. So, either the first interval increases at the expense of the fourth interval, or the fourth interval increases at the expense of the first interval now. So, the sum of these two, if you would call them, that for plus 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 and t minus minus minus, I would just call them as time for t plus plus and the time for which t minus minus is applied. The sum of these two is same. So, that during the middle one pulse, there is some line voltage pulse applied. Here also there is a line voltage pulse applied, and these two is a line voltage pulse applied. So, the widths of the line voltage pulses will not change, but their positions alone will change now. So, this is again what you call as a redundancy, and this redundancy leads to various modulation methods. This redundancy lets you add some common mode voltage now. You can do that 0 state, apply that 0 state either by having all the top devices are on, bottom devices are on, correct, and also for longer time you can keep this on, or for longer time you can apply this state. So, this redundancy, this leads to the application of common mode signal now. So, this is now what is the common mode signal? Any third harmonic you had, that will be a common mode signal now. You have fundamental sign, that is you have this red dotted line, which is the sinusoidal modulating signal corresponding to R phase. Then let us say you add a third harmonic indicated by this blue line given in a dashed blue line. So, this is a third harmonic now. You add this to MA to get what you call as MA star. You see this signal is like this, where the head has gone up, it is like a bent head, it has gone inside down. Where the original sinusoidal signal had a peak, is going out, this is slightly come down, and you can see that the new signal has a lower peak value than the original signal now. So, when I produce such an MR and if phase shift by 120 degree, the sinusoidal, the fundamental sinusoidal component is shifted by 120 degree, but the third harmonic component is unshifted. Because third harmonic is shifted by 120 degree, it means at the fundamental frequency, the third harmonic frequency is simply shifted by 1 cycle time. So, you add the third harmonic to MR and MY and you subtract the two, the third harmonic will vanish, just as the second harmonic vanished there now. So, what you can now do is you can add such a small amount of third harmonic there, and now with this third harmonic addition, what you can do is you get these signals, the red signal, and then you see this green signal which represents the yellow phase, and you see this blue signal that represents the blue phase. These can be compared against a common triangular carrier. You may say, what is the point in doing so? Now you see this red signal, the original dotted signal, has a higher peak, but the second signal has a lower peak value, and the lower peak value is what limits the end of linear modulation. That is, earlier this peak could go all the way up to 1. Now because of this addition, this peak could go all the way up to 1. By the time this lower peak goes to 1, you can certainly see that this dashed line peak, the original sine wave peak, would have gone much above 1, somewhat above 1. So that actually means it is possible for you to produce a higher fundamental voltage with this than you can do without sine addition. Now let us demonstrate this. Now I can write down a few equations here. So if you write down the equation, what I am trying to do here is I am take MR star equals MR plus K times MR, I am sorry, MR is Vm sin omega t, K times Vm sin 3 omega t. I can again say My star equals My plus the common mode component, which is ditto. Mb star is equal to Mb, which is the sinusoidal signal, plus the same thing. Now this is what you do, and this K is a constant, or it can be varied. K is a small number, you can take it as 0.15% or whatever. K equals 1/6 is what would give you the best DC bus utilization. That's it's good to produce, I mean, high amount of AC voltages with whatever DC you gave. That is something we will discuss a little while now. So this is the third harmonic injection, that is K is equal to 1/6 now. I am showing it with K equals 1/6. So you see what happens, I am showing the red original sinusoidal signal. The original sinusoidal signal goes clearly above 1. What I have taken is actually 1.15 or so, that is basically 2 upon root 3. This is 2 upon root 3 is the original sine wave now. And to that I am adding a third harmonic component whose amplitude, this blue thing, and the amplitude of this blue wave is 1/6 of the red dotted wave. When I add like this, what I get is the resultant is what I get here. So I am able to move up to 2 by root 3. My peak of the sine is not limited to 1, but it can go all the way up to 1.15, 2 by root 3 or 1.15. So it gives me 15% additional voltage. With the same DC bus voltage, if I modulate my inverter using such third harmonic injection, where the third harmonic amplitude is 1/6 times the fundamental amplitude, I can produce 15% more fundamental voltage, AC voltage, with the same DC bus voltage and same inverter now. That is one advantage now. So it is like you are increasing the voltage rating of the inverter, without really increasing the voltage rating of the devices that you are really using that, and you can see the benefit there now. And this third harmonic injection also influences the spectral properties. The PWM waveform, ultimately if you produce and you compare, the spectral properties differ with this third harmonic injection now. And instead of K equals 1/6, if you take K equals 1/4, that gives you very good spectral properties, and that is very close to what is conventional space vector PWM, which we will discuss a little later now. So here also what you do is, the same way that we did there, you can add all triplet frequency components, not only third, you can add third, 9th, 15th and all those components you can go about adding, correct. So how do you do that? And you can add them in such a fashion that there is bus clamping. Now what I am trying to do is, you see this blue signal, do you see this signal? This is common mode. I am getting it by subtracting different modulating signals in different regions from either +1 or -1 now. When I add this common mode signal, what happens? I get a resultant waveform like this. You see the red waveform? So it is clamping here. It is not clamping for 90 degrees as it happened in the single phase case, where there are 2 legs. It is clamping for 60 degrees now. The same R phase is clamping for 60 degrees in the negative half cycle. So here the positive top device would be conducting, here the bottom device would really be conducting now. So this is what you do say, I mean whatever conducts in the upper, there is a uniform distribution between the top and bottom devices now, and all the 3 modulating signals are also phase shifted versions of one another. This is a kind of bus clamping that ensures equal loading of all the devices that we were discussing in the single phase case now. So this is 60 degree clamping now. We will discuss this in greater detail in the next lecture, where we will essentially deal with clamping, but just let us kind of familiarize ourselves with various kinds of thing. Now, with the same 60-degree clamping, you can go all the way up to 2 by root 3. Instead of 1, I am going up to 2 by root 3, the fundamental amplitude. And now, you see that my common mode signal looks different. And if I add this common mode signal, this is the kind of modulating signal I get. And without going into over modulation or pulse dropping, I can get. So, I can get this 15% higher voltage here also. And what happens besides that is there is a reduction in the switching loss. That is something that I am able to achieve now. So, there is a generalized version of that. Here you see that the clamping is in the middle 60-degree duration. It does not have to be in the middle 60-degree duration. That can be shifted to the left or right, anywhere between 30-degree to 150-degree, which we will discuss further in the continuous class now. So, this clamping, instead of being from 60 to 90, it can be between 30 to 90, 40 to 100, or even 90 to 150. So, you can clamp it for 60-degree duration anywhere there, and the position of the clamping interval can be changed, and they change it normally for depending on the load power factor to reduce switching loss, which we will discuss a little later. So, this is continual clamp PWM now. What is also possible is split clamp PWM. So, instead of clamping it continually for 60 degrees, it is also possible for you to clamp the 60-degree duration into 2 different intervals, say for 30 degrees in the first quarter cycle and 30 degrees in the next quarter cycle, and so on. So, this continual and split clamping PWM would be the subject of our next lecture. So, this is what I am trying to look at now. So, I hope that you have been followed. So, what we have tried to do is introduce the concept of even harmonic injection in the case of single phase inverters now. It does not have any practical benefit really speaking, but there is no increase in DC bus utilization. You really can't produce higher AC voltage. In fact, the AC voltage you can produce will become lower if you inject even harmonic. So, in that sense, even harmonic injection is disadvantageous in the case of single phase inverters. On the other hand, you can certainly go in for bus clamping. That is bus clamping, if you do, you will be able to reduce the switching loss, and that has been discussed in this particular reference that I am showing here, which is the second reference that you find here, Patnaik et al., that is an investigation into even harmonic injection and pole voltages of a single phase inverter. So, you can get more details of this there, and the other things are available in this third reference now. There is some amount of discussion on continual clamp and split clamp PWM, and we will discuss this in detail in the next lecture. So, thank you very much for your interest in this course, and I hope you will continue to be interested, and thank you very much. Bye.